Okay, let's start. So yesterday we started discussing on pipelining, and I need few more classes to finish this. Oh, can you see my screen? Is my screen visible? Yes, no?
Yes, sir.
Yes, sir. Yes.
Okay. Well, so we were talking about MIPS pipeline, and you have this 5 basic stage. We know about that, right? Instruction fetch, decode, and register, read, execute, memory, and write back. So these stages are being performed sequentially one after another. Now, since since we are going to consider a pipelined implementation, so that single cycle implementation will not be possible. I mean, that will not be any more valid. So you need multi-cycle implementation. And in each small cycle, we finish execution of one component. We have 5 stages, 5 components. So in each clock cycle, we finish one component. So altogether, we need, in order to finish an instruction, we need 5 clock cycles. Notice that, so this is the basic hardware which implements the data path with control for single cycle for implementing some basic instructions. And we have identified that there are portions of the hardware which are responsible for executing the different components. For example, whatever you see here, these resources, they are responsible for executing the instruction fetch part. These modules are responsible for instruction decode and register fetch and so on. So consider this pipeline implementation over single cycle, the basic hardware blueprint. So do you need anything else in this structure in order to implement pipeline in the presence of multiple cycles? I'm not going to add any more instructions, just consider the basic thing. But do I need any more resources just to take care of the presence of multiple cycles? You need something else in order to implement in multiple cycles. Now you have a smaller cycle, right? In each small cycle, in each clock cycle, you are performing one component. So what else do you need in order to implement this? We need some basic resources. Any idea? Just think about
the
it.
interface.
Huh?
The interface between the layers, because like when the decode fetch stage requires the instruction, but by that time instruction fetch will have produced a new instruction. So we need to store the instruction somewhere.
Correct, good. So in between stages, you need some kind of latches, flip-flops, or pipeline registers to store the intermediate value. After processing, each small subcomponent, isn't so? So therefore, so as you see these red lines, you need interfaces or you need interstage latches, flip-flops, or pipeline registers, so that this multi-cycle implementation can be implemented. That means after the first clock cycle, the instruction fetch, this portion would take care of the instruction fetch, and the intermediate results will be saved here. And based on that, the next module will perform instruction decode and register fetch, and whatever whatever the processor does here, those intermediate results will be saved here so that they can be accessed by the next step. And as you move from the left side to the right side, from left to right, another instruction will come and so on. So that's how this pipeline occurs. So this adds some more overhead compared to the single cycle implementation. In between stages, this is very important. In between stages, we need interstage. So we need interstage latch, flip-flops, or pipeline register to store all this intermediate information. All right. So this is a fundamental understanding you need in order to implement this pipeline model. Not only pipeline model, even if you want to implement the multi-cycle model, you need this kind of additional overhead. Okay, you need more state registers or memory as the interface between two stages. All right. So as we discussed last time that this pipeline diagram can be represented in the form of a table like this. So you have this clock cycles. This x-axis denotes time and y-axis denotes the sequences of instructions. So as we have 5 stages, as you can see here. So we observed some basic things. So this is the clock cycle time 5th clock cycle. See, all the modules are busy here, you know. And so therefore, since I have 5-stage pipeline, so this is the maximum parallelism we can achieve. So at most you can have a speed up of 5. So this is a fundamental thing of the pipeline implementation. So the speed up of the pipeline is always limited by the number of stages. So this is one thing. Other thing is, if I look into this consecutive emission, for example, the time here and the time here, the time interval between these two is determined by the time of the interval of the longest stage. So the longest determines it, you know, regardless of the time interval of the other stages. Okay. Fundamental things. So we can represent the time sequences of execution using this kind of table. Each instruction is divided in component stages. And as we can see, there are overlapping of instructions, meaning that all the hardware modules are busy. And each module is executing a particular instruction. Okay. So for example, instruction fetch is executing the last instruction. Instruction decode is executing the last but one instruction, and so on. WB is being executed by concerns this first instructions, and so on. So multiple instructions are being processed at clock cycle 5. All 5 instructions are active in the 5th cycle. Now tell me, we always talk about the balance stages. Balance stages mean the time for executing this. They are made more or less equal. Even if they are not equal, you know, we just wait for them. We just add some delay and wait for that. So why balance stages? Would there be any logistics problem if they are not balanced? See,
like
observe
if one stage took too long, sir, then like in that while more of the subsequent stages will execute, but then there will be not enough data for that to execute subsequently.
Yeah, you are talking about some sort of, I guess, data non-availability. Yeah, that's some kind of hazard we would talk about. But even then, there are other simple things, you know. So if you just look into these boundaries, say you look at the laser pointer here, you look at the boundaries, see that if all the stages are balanced, this boundary synchronizes, right? Because another thing that this emission rate will be determined by the longest pipe, the longest stage anyway. So if you keep them balanced, the logistics become simple because everything finishes in synchronously. So that's why the balancing is needed. So one is the logistics, other is that speed up is determined by the longest stage anyway. So even if some stage takes smaller time, you just wait for delta, so that all the intervals, all the stages take the same amount of time. So there are three things we observe here. One is the maximum speed up, other is the distance with the fact that the longest stage determines your speed up and emission time. At the same time, the notion of the balanced stages. Well, so let us move on, and we have some more terminologies. Now, if we look into up to 4th clock cycle, we have 5 stages, but up to 4th clock cycles, all modules are not busy. So this is called the filling time. Pipeline is being filled here. Here it is full. And then it is the emptying time or draining time. Since the latency does not improve, so therefore, once the pipeline becomes full, then you get the full maximum benefit. You keep on, if the number of instructions increases, and then you get maximum benefit of parallelism. But in the initially and at the beginning, those are extra overhead. One more thing. Let's move on. Yes, so there is one question here. So for example, here you fetch one instruction, you decode another instruction, execute another instruction. So what does it mean for hardware? So we have already discussed that, because since we have inserted latches in between stages, so between two consecutive stages of latches, they can be performed in parallel. So that much of hardware modification you need. Well, now let us look into this instruction types. For example, if we have R-type instructions like addition, subtraction, logical AND, OR, and so on, we don't have any memory operation, right? We have instruction fetch, decode, execute, and write back. We don't need memory operation for implementing R-type instructions, addition, subtraction, logical AND, OR. So therefore, if you construct the pipeline diagram, so it has only 4 stages. It does not have 5 stages, right? See what happens. So we don't need this memory stage. And suppose we now want to pipeline with R-type with load instruction. In load, we have all 5 stages, right? In load, we need all the 5 stages, including the memory. But R does not need 5 stages. So there is a mismatch here, as you can see in the pipeline. If we draw this pipeline diagram, and if we don't put mem there for R-type, there will be mismatch. For example, so add here, I need 4 cycles because I don't need memory. Similarly, subtract, I have 4 cycles, I don't need memory. Load, I need full 5 cycle, right? Memory here. And then I have a logical OR here. Again, this is an R-type instruction. So if ID execute, write back. And similarly, load here again 5 clock cycles. So do you see a problem here?
So in clock cycle 7, the same unit is used twice.
Right, that is not permissible. Because in the same clock cycle, one hardware module can be used at most once. So there is a conflict here, as you can see. I mean, this pipeline diagram cannot be executed properly. So how to resolve this? What is the reason for that you have this kind of conflict? Because for R-type, you have 4 stages. There's a mismatch of the number of stages. Since this is shorter, so the WB, the stage WB conflicts with, interferes with the previous one. Right? So what is the solution then?
We can add a dummy stage for the missing stage.
Yes, just no op. So therefore, having 4 stages, I mean, if it is a purely multi-cycle implementation without pipeline, then it would have been beneficial, advantageous. But in the presence of pipeline, having 4 or 5, is more problematic. Because you need to resolve this conflict anyway, you have to wait. So wait means you have a dummy operation, a dummy stage. That means whenever you have 4 stages, better insert a no op so that all instructions take 5 stages. So there is a conflict of hardware resources here. So solution you have already mentioned, that just enforce uniformity. Ensure that all instructions take 5 cycles so that they become of equal length. And if you don't need some stage, just put no op. And it has no impact on the pipeline throughput. Because making it shorter, you cannot proceed anyway. So in this particular example, you have 3 R-type instructions. You have to insert no op here. So now you can see the pipeline proceeds smoothly, possibly with no interaction. I mean, no conflict. In ideal case, there may be conflicts, of course, because of data dependencies and other thing we will discuss next. But this mismatch conflict due to this mismatch of length of instructions, that is resolved. That problem is solved. Well, so very simple, just common sense best solutions. Similarly, if we have store and branches, for example, store instruction. In store instruction, you have 4 stages. You have instruction fetch, decode, execute, memory. You don't have a write operation here because you are writing to the memory in case of store. So no register write is involved. So you need an insert no up here. And similarly for branch also. You branch, you don't have this kind of thing. So you need two no ops here. Well, so what you have learned so far, the summary of this, pipelining attempts to maximize the instruction throughput by overlapping or by executing multiple instructions simultaneously. And all instruction is better that you design the instruction in such a way that all instruction pass through the same number of stages, including no ops. Speed up is bounded by the number of pipe stages. And in the best case, one instruction will finish on every cycle. I mean, in the ideal case, every instruction, once the pipeline is full, then every instruction and every subsequent instruction will be finished in one clock cycle. And therefore, the speed up approaches the pipeline depth. Each stage has its own hardware units that takes care of that. So again, the same summary, but one thing is I want to mention here that, well, speed up is less than or equal to k. If the stages are not balanced, then you can do a simple arithmetic to find out that the speed up would be less. It will be maximized when there's all stages are equal. Okay, but these are all ideal cases that the pipeline proceeds smoothly. But in actual scenario, there are many other issues that you need to address. One is pipeline overhead. We have just talked about that in between pipeline stages, you have interfaces. That means the stage of pipeline registers or latches. So they add up pipeline overhead. And there are events which are called hazards. It means that the pipeline cannot proceed smoothly. It may wait for some data which is not yet ready. It may wait for something, or what might happen that both of them are wanting the same resource. In that case, you have to, one of the stages, one of the operations must wait for some time or stall so that the hazards are resolved. So we'd see with examples that what kind of hazards are possible and what are the techniques to manage those kind of hazards. So hazards are events that basically reduces the pipeline flow. That just obstructs the pipeline flow. Okay, so here let us consider this example. For example, at clock cycle 5, so these are my instructions, instruction 0 to instruction 4. In clock cycle 5, you see that this write, where do I write back? Write back means I am writing to a register, right? I'm writing to a register file here, and here I am fetching an instruction from of instruction 4. So as I mentioned just now, that once the pipeline is full, then every subsequent instruction finishes in one clock cycle. See this emission rate, So therefore, CPI tends to 1 because every average number of clock cycle per instruction now approaches 1 if you have sufficiently large number of instructions. Isn't so? On the average, so CPI becomes low. Okay, now this WB write back, why to write? Okay, so suppose this is an instruction. Since it is a WB, it is something like load or add, something like that. Assume that this is an addition instruction. Add T3, T1, T2. So which one is the destination register? T3. T3. Now, when the instruction is executed, where from this information corresponding to the destination register is taken? How the machine finds the information of the destination register, from which entity? The sources and destinations are specified where? In the instruction itself, right? Isn't so? So in the clock cycle, in the 5th clock cycle, you need to find out the destination register of this instruction. But this information is embedded in the instruction itself. But in the same clock, but in the 5th clock cycle, now you have this instruction which has entered in the pipeline. So currently your instruction register has information about source and destination of this instruction. Do you see the point? Because currently in the pipeline, we have a different instruction whose instruction is being processed. Or the bits in the instruction field and the information about the source and destination is now processing for this instruction. But I need information about this T3, which enters the pipeline beforehand. And by the time I am processing this is already lost. Have you appreciated the problem?
So how are all these synced? How are all these synchronized?
That's why I'm asking, at this point, so there are latches we have already discussed, fine. But at this point, we need information about the destination register, and the information about source and destination registers, this is embedded in the instruction fields, right? But currently you have, at the same moment, when you are going to write this, at that moment, a different instruction is here. So that means I need to preserve this information, in the pipeline. How do I do?
So we forward the value to like the next stage and the next stage.
Very good. That's the answer, and you have got the correct answer. As I said that, you have a pipeline, you have a register here, latches here. So when this instructions was processed, that information about source, everything about this information, this instruction that were saved here. Now, as we push on different instructions from in the pipeline, those information have to be copied to the next stage of latches in the next clock pulse, and again copied here. So by the time you are here, that information is copied here. Okay. And therefore, in order to see the implementation of process, implementation of pipeline becomes complicated. You need all these hardware resources so as to pass this information of the previous instructions. Just with every clock pulse, you have to push them so that you find out the desired information at the right moment. And therefore, not only you need to have the pipe interstage latches, you should have a mechanism of transferring them information horizontally, with every clock pulse. Got it? So this is a very fundamental issue in the implementation of pipeline. Right? Because otherwise you won't be able to implement this. You won't be able to find out the destination register because we have a different thing here. But that information will be available in this latches. If we look into the latches corresponding to the instruction fetch module, now it is processing something else. I think you got the idea. Okay. So we observe that unless you do this kind of special mechanism, information regarding the destination register ID for instruction 0 is no longer available in the pipeline, because now this stage, the latches which immediately follows the instruction fetch module, that is processing a different instruction. So those previous information should have been transferred sequentially to the subsequent stages of latches. Okay, so you need latches here between stages, between two consecutive stages, and with every clock cycle, what you need to do, you need to propagate the content of the latch forward. Then you would be able to handle this problem. So there are two things: the use of latches between adjacent stages, and not only that, the contents of the latch should be propagated forward as the pipeline advances. So therefore, whatever information you need for processing a particular information, that would be available in your neighborhood. And obviously, this adds pipeline overhead in terms of hardware. And you also need a transfer mechanism, therefore additional hardware. And this slows down the pipeline to some extent. But without this, you cannot execute a pipeline instruction. This is the necessary sort of thing. So as you can see that although my ideal speed up is the number of pipe stages, but the speed up will be reduced because of this different kinds of overhead. Because this would take additional time. It would insert some delay anyway. Well, so these are called pipeline registers, and they are identified. They are denoted as by symbols like this. So this is the pipeline register which separates instruction fetch and decode, and therefore they are identified as IF/ID. This lies between instruction decode and execute, and so they are labeled accordingly. The previous stage and the next stage, the previous stage and the next stage. Now, after write back, you don't need any pipeline register because why do you need any pipeline register here after write back? Actually, you don't need register here because whatever you want to write, you are writing to the registers here anyway. So that is sort of implicit, that we don't need in this 5-stage pipeline. Okay, so need registers between stages to hold information concerning the previous cycle and to pass information forward in every clock cycle. In MIPS, so happens that this ISA is very simple, and the simplicity of ISA help you in designing this pipeline. Since all instructions are uniform and all instructions have these 5 stages, so therefore it is easier to fetch and decode in one clock cycle. And it is easier to make all the pipeline stages balanced. However, in Intel machines, for example, the instructions are complicated. There are starting from 1 byte to 17 byte instructions are there. An implementation of pipeline for these machines, relatively much complex. In case of MIPS, we have a lot of advantages. We have very few and regular instruction format, and we have only load store addressing. That means memory is accessed only for load store. And we assume that memory access here takes 1 clock cycle in our pipeline, assuming that we have an ideal cache. There is no cache miss here. If you have a cache miss, then obviously the pipeline would be slowed down because you have to wait for the data to arrive, data or instruction to arrive. Okay. Now let us move on to the study of hazards. There are many instances or events that might occur that slows down the pipeline and inhibits the pipeline to flow in usual fashion. These are hazards. So these are situations which prevent to start the next instruction in the next cycle. Therefore, you have to wait until this hazard is resolved. Okay. And therefore, obviously, needless to say that it slows down the pipeline. Now, typically, the hazards are classified into 3 groups. One is called the structural hazards. It means that there is a conflict with some hardware resources. 2 instructions are wanting the same hardware resource for some reason. So this is termed as structural hazard. You have conflict regarding hardware resources. All right. And then the most important one is the data hazard. As you see that in pipeline, several instructions are sequentially enters one after another. But one instruction may want a data which is being processed by the previous instruction. For example, you have as a load, and then after following that you have an addition instruction which uses the same register. So you want that data. But the data may not be available when you want it, and therefore you may need to wait until the previous instruction finishes its work. And these are called data hazard. We will show examples how structural hazard, data hazard might creep in. And what kind of other hazard you might think of? Another very important kind of hazard. I mean, you are waiting for something, but that's not yet ready.
So catch miss.
Cache miss. Actually, cache miss is you have to wait, but in computer architecture, cache miss is not considered as a pipeline hazard. I will explain later why. You have to wait anyway for cache miss, but truly that is not a hazard because the memory, this memory hierarchy is not a part of the pipeline. I mean, you have to wait for cache misses, but that's truly not a so-called hazard. There are another important type of hazard, excluding memory. Imagine that instructions are entering in the pipeline one after another. Huh? Suppose, let me give you a hint. Suppose I have a branch instruction and following branch, there is another instruction. So currently branch is being executed and the instruction which follows branch, I mean, just sequential instruction which follows branch, that also enters the pipeline.
So we may need to clear the pipeline from that instruction and then put the next instruction.
Yeah, may or may not have to clear because if the branch, suppose the branch is not taken, then the next instruction will be executed anyway, right? Then whatever has entered in the pipeline is correct. Hmm? You wanted to say something?
No, sir. I just said I agree.
Okay. So suppose you have a branch instruction followed by another instruction. Now, in the branch instruction, the computation of the target address is being performed in which stage? In the execute stage, isn't so? Because we have to compare whether or not the condition is true. So that means in the third stage, it is being computed, whether the branch would be taken or not. Now, by the time the instruction which follows branch sequentially, that enters into the pipeline, because instruction fetch and decode of the subsequent instruction that has already been processed. Eventually, if you find that the branch is taken, then whatever instruction has already entered into the pipeline has to be flushed out because you need to go to the target address. And in order to implement that, this flushing and allowing the target address to enter into the pipeline, obviously you need all kinds of overhead. And this is called what is called a control hazard. So deciding the action of a control, just a branch instruction or jump depends on the previous instruction. Conditional branch. So we would see that how these hazards appear in the pipeline, examples of that, and how to resolve this pipeline in whatever the best solution we can do for handle those. So remember that generally they are classified into these three groups: structural hazards, conflict of hardware resources, data hazard, meaning that you are waiting for some data which is not available. And other one is the control hazard, which instruction would be executed next, whether the sequential one or the target one, that is not yet determined in the pipeline. So therefore you are not sure about what has already entered the pipeline following a branch instruction, whether it will be executed or not. It will be known after some time. Okay, so in summary, structural hazards means attempts to use the same resource by two different instructions at the same time. Data hazard means an instruction source operand yet to be produced by a prior instruction. which is still in the pipeline. And control means your attempt to make a decision about a program flow before the condition has been evaluated. You don't know what will be the next target address. You know. What will be the address of the next instruction? Would that be the sequential instruction or the target instruction? Now, one thing is obvious. Whenever if you identify this kind of hazards, so there are two things. You need a mechanism for identifying this kind of hazards, and that means additional hardware resources. And once the hazard is recognized, then what should be the recovery actions? You know? Now, one simple recovery action is to just simply wait until time passes and the hazards are automatically removed. So, for example, structural hazard, you're waiting for something, let the operation finish, you know, then the resource will be free. Data hazard, let the data be ready. You wait for some time, data would be ready, and then use it. You know. And similarly, control hazard. You know. So the hazards can be resolved just by waiting, inserting bubbles in the pipeline. These are called, we insert bubbles or no-ops or dummy operation in the pipeline. It's also called pipeline stalling. Okay. So there are three things. First of all, the hardware controller must detect the presence of the hazard. And then you should take appropriate action to resolve hazard. And as we discussed a while ago, that whatever the cache misses, you know. Now cache misses can also be handled by using bubbles. Just wait for some clock cycles until the cache returns you the correct value. Now you may need many bubbles here, you know, because if there is a cache miss and then main memory page fault and so on, so that cannot be predicted ahead of time. But these cache misses, they are not truly termed as pipeline hazard. You know, I mean they insert and they cause delays in the pipeline. That is true, just like the hazards, but they are not termed as hazard. They are separately processed. Because in order to handle cache misses, you have to separate the cache hardware and so on, right? That is managed by part of this managed by a memory management OS. If there is a page fault and so on, and if there is cache misses, then it is managed by the cache hardware. Caches are managed by hardware, page fault and etc. Those are managed by operating system, mostly by software, right? So cache misses are truly, they are not termed as hazard. All right. Structural hazard is a very simple example here. So let us consider this 5 instructions, the 5 instructions which enter the pipeline. And here, just look here that this load is accessing in the 4th clock cycle. Load instruction is accessing memory module that you want to read data from memory, and here instruction 3 is instruction you want to read the instruction from memory. So the memory module is being accessed by the first instruction load, at the same time this 4th instruction, which is now trying to fetch the instruction. So if we have a single memory module, for instance, in an implementation, then what will happen? Can you just move through this pipeline, or you have to wait? Because every memory module, as you know, that it has some access mechanism like decoder and so on, read-write bus, an access mechanism, and a memory module can be accessed in one clock cycle one time. So there is a clear conflict, and you already know that how to resolve this conflict. We have already seen that, and that's why we keep separate instruction memory and data memory. or instruction cache or data cache separately. Got it? So this is an example of structural hazard. If you have a single memory module, this causes a structural hazard. And in order to resolve the hazard, one way to do the stall, that means you just push this instruction towards right in the pipeline by 1 clock cycle, so that now the instruction fetch appears here. Again, there may be a conflict with this guy. Anyway, so you have to push it up to maybe here, and that inserts a lot of delay. And that's why you need separate instruction and data cache. So use separate instruction data memory modules or cache. And recall that when you implemented the single cycle processor, since we have to implement, since our goal was to implement everything on a single cycle, there also we have to have this kind of separate instruction and data memory. Okay, so this is an example of structural hazard, but it might there may be more complicated structural hazards if the pipeline is longer. For example, if I have a floating point implementation and I have a pipeline implementation of floating point, addition, multiplication of those kind of operations. So they have many stages, and we might have structural conflict here. We might have structural hazard in the pipeline. So this is a conflict of hardware resources. Either you duplicate or replicate the resource, or you insert stall. All right. So it would cause a pipeline bubble for handle instructional hazard, or require separate instruction or data memory, or separate instruction or data cache for this example. There are more involved and complicated examples involving floating point pipeline. All right, now let us move on to data hazard. And this is a very important class of hazard, and management of data hazard is really complicated. It needs a lot of hardware tricks and very nice concepts are there. So what would be a data hazard? It's essentially, so there are active instructions currently, and they want to access the same memory or register location. For example, I have an add instruction which have 2 source registers, and in the previous instruction those source registers are being updated, but the updation has yet not been completed. Then what to do? Then is kind of data hazard. So suppose you have instruction B which follows instruction A, and the trouble arises, that B wants to manipulate, read or write data before A does. Suppose A is writing a register to a destination. A is writing to a destination register, and the same destination register is being used as a source register here. Now this instruction has already entered into the pipeline. It might so happen, which give an example, that the previous writing has yet not been completed, because writing is completed in the WB phase, write back phase. Before that, this instruction wants to read the data. Obviously, if it does, then it would read an incorrect data. And that's the reason of the data hazard. B wants to manipulate, read or write data before A finishes his job. In other words, this violates this execution order, because we assume that it is implicitly assumed that the operation of instruction A is completely finished before B begins. Okay, let us give you a simple example here. So the first instruction, instruction 0, I have this one. Add $1, $3, $4. So these two are my destination, source registers, and this is the destination register. So this is entered into the pipeline. So when this destination register is being updated, in which clock cycle?
So fifth
clock cycle. That's a write back stage. Good. Suppose another instruction is entered here. Another instruction enters here by, just they are pushed towards the right by 1 clock cycle. Assume that these two instructions, they do not depend on these registers. Now consider this fourth instruction. Here there is an add instruction where the $1 is used as the register 1 is being used as a source register. Okay. So whatever you are updating here, I am going to use it here. So in this instruction, when do we perform this register read operation? I need to read the source registers. When do we perform the register read operation? In which clock cycle? Just count the clock cycle from this side. In which clock cycle register 1 would be?
The fifth.
Fifth, correct. Here, right? Do you see a problem here now? Notice that this instruction is still far away. I mean, it's not immediate. It's still in between. You have 2 more instructions, which may not interfere with the operations of these 2. All right. So already 3 more clock cycles have already passed. So 1 clock cycle here, 2 clock cycle here, and 3rd clock cycle here. Even then, see the destination being updated here, and the same register is being used to source here, and you want to read the source, the same register in the same clock cycle. That's not possible. If you read, you are going to read something else, before updating. Or maybe there is one instruction is trying to write, another instruction is trying to read. It's not possible. So this is a kind of data hazard. You are waiting for something which is not yet ready. Even though there are already 3 clock cycles have elapsed. Between the one, this one, the concerned one, and the current one. $1 is the destination register for the instruction 0, and this is the source register for the 4th instruction. So there is a conflict. Pipeline cannot proceed. If you push this pipeline by 1 clock cycle, it is okay. Isn't so? Now you please tell me that how do I know that there is a conflict here? How does the machine know that whatever destination here is being used as a source here in a subsequent instruction? But if this instruction appears later, then it is not a problem. Because by the time, because that instruction will be pushed a little bit farther away towards the right side, and there would be no conflict. If this appears earlier, again there will be conflict. It is not yet available. How the machine would know? How does the machine know that there might exist this kind of conflict? The destination may not be ready. The source may not be ready. Because the prior destination has not yet been updated. So that's one issue. How does the machine know that this kind of thing is going to happen? And if it happens, how do I resolve it? You see this, and that's why the pipeline controller becomes more and more complicated. Can I detect in compile time?
Yes, sir.
You can do in compile time also this kind of situations. If the target architecture is known. We can do in runtime also, because we have all the information in this interface registers. So if I find that, so there are duplication of the registers IDs in terms of source and destination, we can also determine it in runtime using extra hardware. Anyway, so let us not go into those complications. So how do I detect it? But we have seen that there is a conflict here, right? Okay. Let us see that how do I resolve it? There is a very simple solution of resolving it. One is to push this pipeline one clock cycle towards the right. But even without doing it, we can do one thing. Where do I write? I write to a register file. Similarly, where from do I read? So there are register files, right? So both are CPU components. Now, register access is quite faster, compared to memory. It's much faster. Eventually, what happens? You have clock cycles, and these clock cycles have tolerance of this execute operation, the tolerance of this memory operation, and so on. And we have made all these clock cycles, these intervals equal, balanced stages already. So we have enough tolerance for within one clock cycle. And since the register access is quicker, and the whole clock cycle is not needed, maybe in half clock cycle, I can do read and write those registers. So what I do that is a very simple solution here. This is called half cycle read write solution. So given this hint, can you tell me what may be a possible solution?
So we read at the negative edge of the clock.
Yeah, sort of. You write later, and you write first half and read in the second half. This kind of thing. So it is in the same clock cycle, but you have sorry. Say something. You wanted to say something?
No, sir. I think that was
okay. So the solution is simple, So this entire cycle is not needed because the register access is very fast. So therefore, what you can do that in the first half cycle, you write. So this is our writing policy. Our read-write policy is changed. In the first clock cycle, in the first half of the clock cycle, I always write. And in the second half of the clock cycle, this is the clock cycle interval, total interval. And in the second half of the clock cycle, I always read. That means my writes are always limited to the first half, and reads are always limited to the second half. So if I do that, then between this instruction and this one, this hazard is resolved because they are in two separate halves. However, if this instruction, suppose this instruction was here, then it is not resolved. It would still be there. Because it is being written here and you want it here in backward time. That's not, that hazard cannot be resolved by this half cycle technique. But this particular hazard, this particular situation can be resolved by this half cycle policy. Do you follow me?
Yes, sir.
Yes, sir.
So this is the total clock cycle for this interval. So at this age, in this half cycle, we finish register write here, and in the next half cycle, we finish a register read. So read always follows write. Remember this rule. And by doing this simple hardware changes and utilizing the fact that the register access is very fast, this kind of hazard can be resolved by this half cycle read write solution. Okay, so let me give you a complete example now, whatever we have discussed so far. So I am going to process, so this is my pipeline implementation. As you can see that there are stages, pipeline registers between two consecutive stages. And I'm going to process this load instruction, load T2, 0 T1. So this is my source register and this is my destination register. So currently I'm in this pipeline stage, instruction fetch. So you can see some shading here in the instruction memory. The half portion is shaded here. Here the half portion is shaded. I guess you can now tell me what is the meaning of this this legend. So in instruction fetch, what you do?
So we read from the instruction memory in the second half and write to the pipeline register in the first half.
Yes, correct. So that's why this second half is here shaded and the first half here is shaded. The second half shaded means you are reading here and the first half shaded means you are writing into the pipeline registers. So that is that actions you are performing in when you do the instruction fetch. Okay. So now the next instruction decoding. So as you move, so this now copies, so now, the instruction decode means you have to read this information about the previous instruction. I mean, this current instruction or the next instruction has already entered here. That's not shown here, correct? Okay. So currently you have to read the registers. I mean, you have to read this file. So that's why the second half is shaded, and you are, and here also the second half is shaded. You are reading from the registers, right? And then you copy this information in the pipeline register. So in the first half. So that is the meaning of this shading. And you go forward here, so then in the execution fetch, you compute the address and the shading is done appropriately. And then you access memory. Okay. And again, when you are reading memory, so in this, that's the second half cycle, and you are writing here in the pipeline registers in the first half cycle. Okay, so now after write back, what I need to do? I need to update the destination register. Where is the destination register now? The register file is here. Okay, so in the write back stage, I am now here. Memory has been read and that content of memory is copied into the pipeline register here, into the second half cycle in the pipeline register. Now I need to transfer the content of memory to the register file here. I have to write the data here.
Excuse me, sir.
Huh?
Sir, here if I am writing the I am reading the data in the second half and writing the data in the first half, then how are we getting the data?
Where?
So
No,
here
no.
in the write back stage.
Data means, the data is already in the register, So you access the register. Your access is limited into the first half or second half, but it's the same register,
Okay.
But here we have another issue. Now I have to write the whole stuff into the destination register, which is here. But because by the time different instructions have entered here, So if I directly write it, you are going to write to the wrong destination. So as I mentioned that we discussed this earlier, that everything has to be transferred about source and destination from between the subsequent. We need to move that information forward. And so if I just write it here directly, then you are going to write, incorrect information. So what you need to do is to pass this information about the destination as the pipeline moves towards the right. And from this set of registers, you will find the destination register and correctly write it here. Do you see my point? And that's why, this entire information for the construction for a particular instruction has to be moved from one pipeline stage to the next pipeline stage. Then only you would be able to write to the correct destination. Now, when you are writing here, something else has entered into the pipeline. So therefore, you should not look here. You have to look at the information about the destination registers in this stage of the pipeline register. But this is very important. You follow me? Or if you have doubt, huh? Okay. So all you can see that by simply this first half and second half anyway, but this management is not so easy. There are a lot of hidden tasks that you need to perform in the pipeline. Okay. Now let us look into another case of data hazard, and this occurs more often. So as before, we have the same pipeline diagram. This represents time, and we have this consecutive clock cycles. The first instruction enters here. $1 is the destination register here, and this is being updated here. Next instruction is a sub instruction, and this wants $1 as the source register. Okay. So $1 is being register 1 is being updated here, and you want to read the content of the register here. This is the instruction decode and register read. So your register is being updated in clock cycle 5, and in the subsequent instruction, in the next instruction which has entered into the pipeline, you are reading the input information, the source information, in clock cycle 2. Clearly, that's not possible. If you read IDR, if you read this register, you are reading something else. You are reading garbage. So this is a clear case of data hazard. These two instructions are consecutive. Okay, consider another instruction here. Here also the same problem. You are reading here, but updation is being done here. Still, there are conflicts. How about this? This I have shown in blue, green. This is destination. This is source. Is this okay or not okay?
Yeah, this is okay.
Yeah, by the previous technique, right? Half cycle.
Half cycle.
Correct. Also okay, right? Okay. Now let us see. So this is shown in red. It is being updated here, and you want to write it in the second half cycle here, but in backward in time, not possible. Similarly, this is backward in time, not possible. This one is okay because it's the first half cycle in the second half cycle, so towards the right, and similarly this is also okay because this is being in the 5th clock cycle, this is in the 6th clock cycle. No conflict here. So for these two instructions, there is no problem, but there are problems here. As I said earlier, that in order to resolve this, you may push this. How many pushes I need? If I don't do anything, only push.
2.
2, yes. So that this guy appears here. And then by the half cycle problem, you can half cycle technique, you can resolve this. So you need to push this guy by 2. And similarly, this will also be pushed by 2 and everything will be resolved. So a pipeline will be stalled by 2 clock cycles. Okay, so that's the simplistic solution. Is there any other solution you can think of? This is some out of the box solution. There is a very nice observation here, which let me give you a hint first. You forget about the pipeline stages. You consider the time instant when this destination is available, and you consider the time instant when this source is needed. Just forget about the pipeline. I mean, when it is the earliest time it is finished and the latest time you need it. Where is those time points? When this computation of S2 plus S3 is available, I mean done, I should not say available, when it is done.
3rd clock cycle. 3rd clock cycle.
3rd clock cycle, yes, at the end of the execute stage. I'm not yet written to the register, but at the end of the execute stage, this is available. And since we have pipeline interfaces or pipeline stages, I have pipeline registers here. So at the end of the 3rd cycle, the value of this register, updated value, is available in these pipeline registers. Do you agree with this? Because the execute is finished after 3rd clock cycle and the result will be stored in the pipeline register. So therefore, the value of $1, updated value of $1, even though it is not copied here, but the updated value is still available in the pipeline register. Yes or no?
Yes, sir.
When do I need it? At the beginning of the 4th clock cycle. Because I need to perform this execute. Forget about reading it, Just think of in terms of the pipeline register. You think in terms of pipeline registers. Don't think in terms of the regular register files. So you need it here before the execute stage, right? That means the beginning of the fourth clock cycle, it is already in the pipeline register. So if we have some hardware mechanism of transferring the content of this register to the input to the execute file, to the input to the execute operation, execute module, then you are done bypassing the register files, because registers are already there in the pipeline registers. This is a very clever technique, It will be written to the register file anyway in due course. But before that, if my pipeline hardware recognizes that I have an instruction which immediately follows this, by some mechanism, if I can transfer whatever pipeline register value you have here at the output of the execute module, that should be transferred to the input of the execute module. And that's why you need a data path connection like this. So here are conflicts, and this is dependencies. These are backward in time because the necessity is here, supply is here in regular sense. So demand is here, supply is here. Demand cannot be in the backward time. So therefore, this is called data hazard. But we can resolve this way in this diagram. So in the conventional sense, there is clearly hazard. And these two are okay by the half cycle case. And okay, so one possibility we have already discussed, that's push them. How the stalls are, 2 stalls are needed. So another question is here. We'll come back to that issue later. Just now, let me just finish this. So here is another question, that how does the machine decide that the 2 stalls are needed and how it could be implemented? Okay, so that may be done in compile time or run time. So that's just by pushing. And the most important thing is, is to do some kind of, okay, let me just skip this slide and I'll show you. Okay. So this is what I'm going to discuss. The same example, this is the destination here, and the next instruction is the source here. One possibility is to just push them insert bubble or stall. The other thing is, as we discussed, that there are interstage pipeline latches, and at the end of the 3rd clock cycle, this execute part is over. And at the beginning of the 4th clock cycle, you need it actually. So let the content would be updated here and later on. We are not bothered about that at the time being, but in order to make this content of the pipeline register, which is here, available to the input of the execute stage here, I insert some extra data paths. And this is called the forwarding, fixed data hazard by forwarding results as soon as they are available and to where they are needed. Because the supply is already done here, demand is here. So the demand follows the supply in time. And in this case, we can implement this. How? Okay, so from this pipeline registers, this holds this data. This is the interstage pipeline latches. So that data, if I want to make it, if I make them available at the input to this execute, so then it would be done. Now notice that this execute and this execute is the same hardware module. So therefore, moving the data from output of this execute to the input of this execute means you are actually moving the data from this output to its own input. This is a very important thing. Whether you please check it on whether, let me know whether you follow this. Suppose I have this extra data path mechanism which allows the output of these pipeline registers available to the input to this execute stage. I mean, its output is fed back to the same input, its own input, of course, through the latches, through the pipeline registers. If I have this mechanism, then when this instruction is being executed, the destination register is updated in the pipeline latches. And when this enters into the pipeline, I know that this is needed now. That data I would make available here to the input to this execute phase. And the other source register is already read here. So this execute can proceed. So without inserting any stall, just by inserting an extra backward data path here, we can resolve this problem. And this is called data forwarding. So there is one interesting thing. We are forwarding data in time, because as you can see that the data is available here and you are forwarding in time, But the data path that goes towards the backward, because from the output you need a path from the input. So it is forwarding in time, but backward in space. Please let me know if you have any doubt or question regarding this slide. And how it has been resolved. Are you convinced that this hazard can be resolved by this? Or is there any issue which you do not agree with? Okay. So what is the technique in short? What action or what implementational changes we need to do?
We have to add a feedback mechanism in the execute stage.
Feedback data path. Huh? Feedback data path from the output of the execute stage to the input of that execute stage. So this entire 32-bit data is available. And moreover, we need to identify this kind of situation. Then only we would activate this data path. So the pipeline controller has a lot of things to do. It needs to identify that you have a scenario like this. You have this source and destination sort of thing. And you need to activate this feedback data path accordingly. I mean, you cannot do it all the time. If you do it all the time, then you are going to have a wrong information. Because suppose instead of having $1, you have something else here. Then the source registers are completely different. So in that case, this backward data path need not be activated. You need to read the content of those information from here. So it will be activated only if this one of the destination, and one of the sources is the destination of a previous instruction. And the corresponding write back operation is yet to be performed. So this is data forwarding. It's called data forwarding because you are forwarding the data ahead of time prior to writing to the write back stage. But remember that the data path, actual physical data path, that goes backward in space. I hope you understand the duality between these two. This is forwarding in time, but backward in space. Okay, so this is a very important issue, and it shows that using this forwarding technique, using this additional hardware and pipeline overhead, you can simply resolve this. A lot of hazards here, data hazard. Otherwise, you need to do you need to insert stalls with 2 cycles. So you can save two stalls in this particular case. However, pipeline control becomes much more complicated. But that would be taken care of by the hardware you are going to design. And so we did not as far as the time is concerned, we are done. So this is summarized as it's called forwarding, or alternatively known as bypassing. Here the idea is the result is already computed in the system. The result is already available in the system before you really need it. If you just forget about the write back and all kinds of register file updation business, but somewhere in the pipeline, in the pipeline registers, the data is already available, which I need in the subsequent instruction. So let us not wait for it to be formally written in the register in the write back stage. Before that, you can use it by inserting some extra data path from the output of the ALU to the input of the same ALU. You need a mechanism for implementing that. So here this is summarized again. You have add, you have a subtract followed by add. So I'm not waiting for when this write back is implemented. Before that, I know that following the execute stage, the data is already available in the pipeline register here. All I need to do is to make the data available to the input to the execute stage, that means to its own input, and that path would be activated. This need to be active. That backward path need to be activated when I process the next instruction, which has entered into the pipeline, and it requires it has a source which is the same as the previous destination. So in other words, data is being forwarded from the output of the execute stage to the input of the execute stage in time, and going backward in space. All right, so this is the summary of what is called the data forwarding technique from execute to execute stage. So what do I need for the extra hardware then? So this is your register file here, and this is the memory file here, and this is the ALU stage, execute stage, and these are the pipeline stages, pipeline registers. So I need an extra path from the ALU output to the ALU input. ALU output means the ALU output is stored in these pipeline registers. So what I need is a backward path through the multiplexers which are already there in the system, so that this information might be available from this register file. At the same time, if needed, if the source of one instruction is the destination of a previous instruction, then we need to activate this path, so that the output of the ALU, the data which appears at the output of the ALU in the previous clock cycle can be used as the input to the same ALU in the next clock cycle. And since in ALU there are there are two inputs, destination source 1 and source 2, you need data paths leading to these multiplexers. You need 2 data paths, separate data paths. Of course, and whether or not this forwarding unit is to be activated, you need an additional hardware. And you can see that there are inputs coming here and from the different sites that determine whether there is a conflict of the source and destination registers. And accordingly, it generates the control signal to activate this MUX, so that this data path is activated and the information regarding here of the previous destination is made available to as the source of the next instruction. So this is called data forwarding from execute to execute stage. Are you with me?
Yes, sir.
Okay, so let us now extend this idea a little bit. Previously, we have subtraction instruction, two add type instructions, one after another. Subtract instruction following an add. So now the first instruction is load, second instruction is subtract. I have replaced the add instruction by the load instruction. And again, I have another instruction here where this is used as a source here. So this is the destination and source in the next instruction, source in the subsequent instruction, and so on. So you please tell me why I have shown this in, when do I need it? Is it green? It should be, green means it is okay, no hazard. Red means possibly a hazard. First of all, you tell me whether this can be resolved or whether between these two things, is it resolvable or not? Are they resolvable or not? By some techniques also. Without inserting any stall. Because stall is a straightforward solution. First of all, just look into the same thing, when this execution is done, when this is available, and when the supply is needed. Forgetting about writing into write back and so on. Just in absolute time, when the data is, when the supply is available, and when the demand is needed. After which clock cycle this data is available?
Fourth cycle.
Fourth cycle in the pipeline register it is available. It is not yet in the write back. It is not yet in the register file, but it is available in the pipeline registers after the fourth clock cycle. Where do I need it? When this demand comes?
Third clock cycle.
Okay, so data is available earliest by the fourth clock cycle and required latest by the third clock cycle. Is it possible? By forwarding or so? How do I forward? It is available at the earliest, it is available in the end of the fourth clock cycle. And this is required in the third clock cycle. It is backward in time. So even if you set up extra data path, would that serve? How can you go backward in time, In the previous example, the data path helps only if the demand arises after the supply, Isn't so? So supply is done at the end of the fourth clock cycle. Demand is at the beginning of in the third clock cycle. So it is backward in time, no matter whether you set extra data path or so, it's not possible. How about this? When do I need it?
The beginning of fifth clock cycle.
here, right? I want it here before this execute stage. And by the time this memory operation is over. So it's forward in time. I mean, supply is before the demand is required. However, in order to do this, in order to make this data available here, what do I need? I need to set up something extra, you know. This data is available in which pipeline register? Following the memory stage, right? And this is required before the execute stage. So what kind of extra data path do I need to set in the backward direction? Just extend your previous concept, your previous solution. What do I need to do? If I set this data path from the memory output to the execute input, would that help? Subsequently, other instructions are also entering into the pipeline with the same source register. The last two are no problem. The half cycle, you know, it is already available in the WB of the first one. So this is already done. This is done. This is, as I mentioned, this can as far as the time is concerned, this is okay. Because this is at the end of the fourth cycle, this is at the beginning of this cycle. But I need to set up a data path from the output of the memory to the input of the execute stage. However, this is not possible. No matter what data path you set, it is not possible because the demand is before the available supply. This is backward in time. So in order to implement this, green arrow, I need to do something extra in hardware just before what we did in the case of execute to execute. Here I need memory to execute. So you need another set of forwarding from memory to execute. However, regarding this, because you have backward in time, one stall is inevitable that you cannot avoid. Do you agree with me?
Yes, sir.
Because it conflicts with the demand supply synchronization. You know. There should be an order between the demand and supply, right? If the demand follows in time, if the demand appears after supply, then it is possible by doing some extra hardware. Otherwise, it is not possible. So in this example, in the subsequent instruction, the stall is inevitable. And this we can resolve, however, using some extra data path. In this particular case, I don't know. I mean, if we push it, maybe it would be automatically resolved. Let us see. What you can do that since this push is, an extra clock cycle stall is inevitable here. in order to resolve this hazard, you have to push this everything towards the right by 1 clock cycle. So here stall is inevitable, and then you can reorganize the other things to other data hazards will be removed by the forwarding technique and the half cycle techniques. So overall, you can compute that how many clock cycles should be needed. So there are, how many instructions are there? The first one would take 5 clock cycles. Then in the ideal case, we should have 5 plus 1 plus 1 plus 1 plus 1. So 5 plus 4. So 9 clock cycle would have been ideal, but this conflict is, this hazard is inevitable. So you need to push this everything. So by 10 clock cycles, you would be able to finish everything, including the stall. Okay, let me just show you. We will go through this again. Let me just show you the hardware first. So as we said that we have forwarding, so these are the different pipeline stages. And from execute, from the output of the ALU, we need a mux here, you need a data path here to take care of this data hazard. And similarly, if you have a load instruction followed by an preceding an part type instruction, then you need, need extra forwarding also, extra data path from the memory output to the input to the ALU. And there is a hardware forwarding unit which takes care of the recognition of those instances where this conflict may arise and what kind of data paths need to be activated. So overall, this is a discussion on data hazard. Let me. Yes. So just looking into the previous example, the same example here, load followed by subtract and then and or etc. So you need a bubble here. So that the demand now becomes later than the supply. Here this is updated after the memory stage, and this is needed before the execute stage. So if I just push this by 1 clock cycle, then the demand follows the supply. And if you have extra data paths from the memory to execute, then we can implement this. This is by virtue of half cycle, and so on. All other conflicts are resolved. So we want to say that there are some hazards which cannot be eliminated by data forwarding also, because if the demand appears before the supply, then you need to insert stall anyway, because data cannot be made available in previous time before it is generated. So in summary, forwarding is a technique that helps you to resolve the different kinds of data hazard. And we need a hardware mechanism to recognize this presence of such possible hazard and appropriate data path activation in order to resolve that, or insert stall. Some of the data hazard, as you can see, are inevitable, and therefore stalls are necessary, essential. so in summary, you can represent this using a simple diagram like this. So if you have load here, you have these 5 stages following the subtraction, the same example here. You have these stages and so on. As you can see, this here, this R1 is a destination, this is R1 is the source. So this is available here after the memory stage, but you need it before the execute stage. So it is not possible. So then you may insert a stall here. You may insert a stall here also, but you may insert a stall here also. It doesn't matter. All you need to do is to push this execute stage after the previous mem stage. But even then, I need the extra data paths from the memory output, that means from this pipeline registers to the input to the execute stage. Okay, those additional data paths we need, which you have just shown. In the regular pipeline, those data paths are not there. So in the presence of those extra data paths, forwarding paths, and if one stall is inserted, all the hazards here can be resolved. And in some diagram, you can see that bubbles are shown in horizontal direction, right? So horizontal bubbles and vertical bubbles, this is just a matter of representation. They serve the same purpose. Sometimes you show that everything these are all bubbles, and this instruction follows that. It's same as they're doing that. So a different way of representing. So you have any question up to this point regarding data hazard or so? This thing is a little complicated, I mean, you need to go through this material a little bit more carefully and to see, to appreciate the complexity of various situations and how they are resolved. And in summary, this is called the read after write, because you have an instruction, you have previous instruction where the destination B is updated. So the previous instruction is trying to write something, and the following instruction you want to read that same register. So that's why it is called read after write. Raw hazard. So instruction I and J follows the instruction. So this is the destination register and this is the source register. So obviously for proper execution, if you want to read this, the previous you must have to know the updated value of the destination register. If not, then it will be executed incorrectly. And that's why the hazard arises. And this is called, the example which you have discussed earlier, this refers to what is called the read after write hazard. So instruction J tries to read the operand before instruction I writes it. And this is caused by data dependence. So this is one of the type of data hazard. We will discuss about more data hazard later on. So I'm going to stop today. You have any question or concern regarding this? We'll continue with more examples in next week. Well, this Thursday is Diwali, so there's an institute holiday. There will be no class. Please enjoy the Diwali. Happy Diwali to all of you. And I think Professor RSC has already announced this one, right? Regarding the final test.
Yes, sir.
Okay, so just note that this is 15th November, the same time, 12 to 2, and the coverage is whatever has been covered by RSC and processor design, which was covered by me after the second exam, and pipelining what we are discussing. Okay, so please let me know if you have any question or doubt regarding today's discussion, and we will continue next week. So if not, let us stop the class and enjoy the Diwali, and we will meet in the next week.
Thank you, sir.
Thank you very much.
Thank you.